All right. Yeah. Okay. I can hear myself as well now. Right. Clash, a practical Haskell to circuit compiler, unlike all the other Haskell to circuit compilers. No, I have no idea. It's more that I very much focused on lots of practical issues. You'll see by the end of the talk what I mean by that. So Clash, it compiles a semantic subset of Haskell, so not the regular Haskell that we all know, but a semantic subset. And it's a very early GHC API user, I think. We presented our first implementation at Haskell 09. I think GHC API is perhaps GHC 6.6. I'm not really sure anymore. So we started 6.8. So anyways, long time ago. So when you program in Clash, so what do you get? Well, you get base, then, right? So that's what you're used to. You get the Clash prelude, which contains RAMs, ROMs, PLLs, mealy machines, all kinds of things that you want to use when you do circuit programming. And then you get dependent Haskell. And we, as in the royal we, really want dependent Haskell. And because I don't like to prove that A plus B is equal to B plus A, you also get like 3 type checker plugins in the mix as well. Yeah, you really need this all. And you can use your own packages, right? But you have to turn on 2 flags. You have to say expose all unfoldings, because Clash is a whole program compiler, so it needs all of your core. That means all of your Haskell needs to be in the interface files. So do need expose all unfoldings. And also no worker wrapper, because the worker wrapper transformations tries to look into Clash's primitive types and extracts the integers out of its numbers. It's very annoying. So yeah, also no worker wrapper. So that's if you want to use Clash and want to build on top of things. This is what you get. So I said semantic subset. So you get all of Haskell except, oh wow, recursive types, recursive functions, no side effects, which is fine, and some semantic things, no GADT pattern matching. However, I said, I focus on the practical things. You do get support for fixed size lists. So that's where the dependent Haskell comes in. And it has maps, folds, functions that you want to do over these lists. You do get them, and the compiler has built-in support. So you can still do all functional, direct recursion is the functional programmers go to. You just use higher order functions and you'll be fine. So this is the semantic subset. Yeah. But you can still specify quite a lot, even if you miss out on all these things. So how do we, so you have combinational circuits like, multiplication and addition, but you also have things that have state. So how do we model state? In Clash, we use streams. We call them signals. And signal has, the straightforward functor and applicative instance, and then you have the lifted num instance, which is just lift A2 of all your operations. And then we have the register function, which introduces memory, basically, and it takes an initial argument and the current stream, and that prepends the thing in front of it. So that means like, well, I'm pushing all of my streams to the future, so I have to remember it. So this is why it introduces state. If you look carefully, and this is what the user gets, you can't, as a user, you cannot get to the constructor of streams. You only get like the type constructor, not the data constructor. And register is no inline. I don't want GHC to inline register either, because I'm going to recognize it and put an actual memory element there. And you'll see later why it's also very important that you don't get access to the constructor. So I'll present a very simple circuit that you can build with Clash, which is a multiply and accumulate circuit. So you have 2 inputs, X and Y, and then you use the register function to to introduce some state because we want to multiply and accumulate. So we have a register with an initial value of 0, and its input is going to be accumulator prime. And how is accumulator prime being defined? Well, it's the output of the register accumulator plus, x times y. And of course, this uses the, the lifted num instance. And what you can see here is that working in Clash, in this subset of Haskell, you're doing lots of tying the knot type of recursion. And for people who are asking, should Haskell be strict or should Haskell be lazy by default? Clash's version of Haskell will always be lazy by default, because if you have like strict tuples or something, you're going to tear everything down and you'll just get exception loop everywhere. So Clash's Haskell will always be lazy by default. So yeah, if you want to get like a feel, I've had people come to me like, yeah, functional program always felt like it's like data, when I see a functional program, I think of data flow and how things flows through it. Well, that's exactly what you're doing in Clash. You're describing these graphs and how things fit together. So a bit of the details of how does Clash actually translate signal. Oh, wow, this is where we cheat, right? So Clash replaces the normal fmap and pure by these versions, which basically says, well, if I have a function from A to B and I get a signal of A, I can just apply that function to A and not care about the underlying stream at all. Because you don't have a user will never have access to the stream anyway, so I can just build my graph like that and not care about it. And then inside Clash's core view. So in GHC, you have core view that can look through new types and can look through function types. Or Clash's core view can also look through signals. And this is why it's important, why the user should never use the constructor of signal, because that will be very confusing. Because if your core view wants to see an integer, and then suddenly it sees there the stream constructor, like, huh, what's that? I don't know how to deal with that. So that's why you should never have the stream constructor. So this is how the Clash compiler sort of cheats. It doesn't have to deal with these signals at all. It just looks like all of the other pure functions, or functions not working on signals. So why do you want to, why would you want to actually build?
Actually,
yeah?
So to just clarify, so when you compile, you are essentially assuming that signal is just the identity functor. Is that?
Yeah.
That's,
yeah.
And
yeah.
You
Basically.
define everything with that assumption. I see. Okay.
Yeah. And it's worked out.
Yeah.
So when you're building a circuit, you might, why would you go there in the first place? Well, probably is power and everything that's derived from it. You don't want 20 or 30 watts in your pocket or on your wrist, right? So power is the main reason why you go to a circuit. And so, but there's also other aspects to the developing a circuit, which is area, how large will your circuit be, and clock frequency, how fast will it run. And I will go now over some of the details within the Clash compiler that focus on area and clock frequency, because actually it's quite difficult to have any effect on the amount of power. And so that's really tricky, but I'll give a sample of some of the optimizations that Clash does to improve the performance of your Haskell specification seen as a circuit. So I'll focus on area and clock frequency. So this is really about the cost model. So we have, thanks. We have cost model. What's the cost model that you should have when you look at your Haskell, right? So basically, transitively from your entry point, all functions will be inlined. Your primitives will have a primitive or unit amount of area. So your multipliers and adders will take up a fixed amount of space. And memory elements, of course. And another important aspect is that any form of pattern matching will take up space as well, because that will turn into multiplexers. So, but only, of course, pattern matching on some types. Product types are basically free. Basically, in Clash, everything is unboxed. You don't have So pattern matching on products is completely free. And very important is that if you look at the case statements, all of your alternatives of your case statement will be simultaneously present in your circuit and simultaneously calculating. It's just that the multiplexer will only pick the right answer, the one that you actually wanted. And this is very important for the space usage. Because let's say we have a function f, which is called twice in your alternatives, then this function f will be present twice. And so it will double the amount, even though only one output will be used eventually in the circuit. So of course there's a optimization in the Clash compiler which makes sure it lifts out f and then does case statement on its arguments, dependent on the case statement that we had originally, and then its argument is used inside this case statement. So this is just one of the optimizations that Clash applies to make sure that your circuit doesn't use as much space, basically. And this is all because it does all the this parallel, speculative parallel computation of your case alternatives. So another aspect that you want to deal with is the layout of your data types. So let's say we have either AB, and then one of them is a word 4, and the other one is a word 2. Then one layout that you probably would think of is that you use the top bit for to determine whether it's right or left, and then you use the other bits for the two fields, and they would overlap in your representation. So this is the, let's say, smallest representation you can think of. So let's say we have a function f that if it gets a right, then it multiplies by 2, and if it gets a left, it adds 1. And then we have registers with f in between. So let's say we implement registers. You get 5 registers. Then the times 2, you get, let's say, your elementary times 2 or plus 1. And then, so pattern matching on right or left, it has to choose between those alternatives. And choosing will introduce these things called multiplexers, and they take up space as well. And then you have the final register. So this adds space, but more importantly, and then if you have an alternative between a don't care and something else, the multiplexer can be optimized away. So this is the eventual circuit that you get. Those multiplexers will disappear. And so I said clock frequencies, how is clock frequency determined? So once you have registers, all the stuff in between, the more stuff you have between registers, the slower your circuit will be. So how slow will our circuit be? Well, so we're going to check from the registers on the left to the registers on the right. So we see, well, we take one step, we either get to the multipliers or the others, so that's 1. And then the multiplexer there is 2. So this circuit is now 2 deep. And so that's because we picked this very packed representation. Another alternative would be to trade space, to use more bits to get a faster circuit. So what we do there is we use 7 bits, and we use the top 4 bits for one field, and then 2 bits for the lower field. And because then we end up with a circuit like this. And as I said earlier, if you have a multiplexer between something that's useful and a don't care, then you can optimize those multiplexers away, and you end up with a circuit that has just a logic depth of 1. So this circuit is faster than the other one because of the amount of stuff between the registers, but it does use a bit more logic. It uses more registers. On the other hand, it doesn't have the multiplexers anymore. And so there's heuristics there. Well, there aren't heuristics yet. I want to add them. But there could be heuristics there. And you could probably measure as well. And so how does that work in Clash? Well, you can say, I want to annotate the type either word 42. I want to say that it uses 7 bits. And then I want to say, well, the constructor left, I want to use the top bit to do the 1, or to the constructor. And then here's the value. And then you tell for the field which bits it should use. So these are bit masks, basically. So yeah, this is, so you can, so the, this is the default behavior that you have in Clash. So the data type representation, but you can override it with your custom bit encoding. So yeah, these are just, so I've always really focused on performance and this kind of thing, but also on the practical side. So yeah, Clash has been in development for 9 years and still no support for recursion. However, I did focus on making it easy to install using Cabal or Stack. We have extensible primitive operations. You can add those in line with your Haskell, and you can teach Clash about new primitive operations. You can call Verilog, which is let's say the low-level language that Clash actually produces. You can call Verilog directly. So instead of inline Java, we have inline Verilog. We have bidirectional signals, so you can use a port of both an input and output. We have DDR signals, waveform generator, multiple clock domains, all kinds of things that you need as a circuit designer. And nobody complained about missing support for GDT pattern matching, but calling inline Verilog was pretty high on the list, because that means you can work as a team, one using Clash and the other one using Haskell. So that's much more. So that's always been my focus, to focus on all these practical things. I quickly want to thank the team at QBA Logic, Jan Martijn, Leon Mulus, people at Myrtle Software who've been using Clash in anger, probably 20K lines of code at least, all Clash, and they're hiring as well. They got a large funding round. Our large corporate anonymous sponsor, which has been supporting Clash for the last 1.5 years, and the community people you see there, and of course the GHC devs, because the GHC API has been instrumental to this work in Clash, and was the way to make a static compiler. That's it. Thank you.
Maybe I missed this, but I'm a bit confused why Clash has difficulty supporting recursive functions, but not recursive let bindings. Well, what additional challenge does recursive functions add on top of that makes it difficult to implement Clash?
So as I said, so when you look, so the cost model is all your functions will be inlined, and so so if there's no bound on your recursion, then it will basically means it would have to inline forever. And let bindings is just, if you look at it from a graph point of view, then your let binding is just basically an endpoint in your graph that you just loop together. So that's what makes it, the recursive let binding easier as opposed to recursive functions.
So could you apply that same reasoning to recursive functions in some way? Like I know that GC currently does not do this, and will just try to inline everything and it doesn't work out. But like, could you post facto do this kind of analysis for recursive functions?
So the issue there is that currently in Clash I decide that, so we have this data type signal, these streams, and I say that basically that happens in one clock cycle. And so if I then add, say, well, this recursive functions is also going to take multiple clock cycles, that then doesn't match anymore. So if I turn it into an iterative process that let's say a recursive function takes multiple clock cycles to calculate a function, then that doesn't map anymore. That I already decided that everything that happens within one value of the stream takes one clock cycle. But that's just because, so I've decided that one element in the stream corresponds to one clock cycle, but it wouldn't have to actually. I could set up a more asynchronous handshaking thing as well. But that would be future work.
If I develop in this Clash, can I share code with Haskell? Like have some files written in Haskell that's conformant to Clash and have them shared between some Haskell project and
Yeah. It uses GHC as a front end. So it's the Haskell. I know some people who just use the Clash prelude to do modeling of circuit. They're not interested at all in actually producing a circuit. They just want to model it. So yeah, you can just use the prelude right away and the plugins, of course.
So you said the G-line of functions. So when you gave the example of the case statement with the duplication, you named the function. So wouldn't it be inline back again?
So it would be inline. So you mean this one?
Yeah.
So it will be only inline once, right, at F. So not the binding won't be inline, but the definition of F will be inline. Okay. So you should imagine. So in terms of cost, you should think of it as F will be the body of F will be there instead of a reference to F.
You mentioned everything's on blocks. Is everything also on query, or can you handle partially one function?
Yeah, so the only limitation is that the entry point, let's say main, should be monomorphic and first order. And then you can use, and then it does sort of like defunctionalization pass, but not really. It turns it into actual. It doesn't use data. It doesn't use this. Do the standard thing of defunctionalization where you create data for your function and actually does all transformations to make it first. It does more. It specializes functions on functions.
Okay. This function, this optimization, you do it like always automatically, or does programmer have some control over it? And also, you could not only this thing commute, but also your register you could commute with some register-less logic. Is that kind of optimization done to make like pipelines even length or something like that?
No. So currently, this transformation is performed on some heuristics. So there's no control, and this balancing of registers is done in downstream tools. So there's the tools that consume the Verilog code already do this balancing, and so it would be kind of, I don't want to re-implement that in Clash, basically. All right. Thank you.